next speaker, Dr. Dan Aronoff. And Dr. Aronoff is a research associate with the Laboratory of Economic Analysis and Design, Department of Economics here at MIT. Prior to LEAD, Dan was a research scientist at the MIT Media Lab, where he worked on a digital currency initiative. Dan has authored 2 peer-reviewed books on the 2008 financial crisis. I just checked it on Amazon, 5-star reviews for each. And he has a wide range of areas where he works on. His research focuses on digital currencies, game theoretic analysis, consensus protocols, and the design of trading mechanisms to enhance market performance. So today, Dan will delve into the world of privacy-preserving cryptography, such as, don't want to steal your thunder, but homomorphic encryption. So let's hear it for Dan Aronoff. Put this on.
And this will,
Don't use that.
okay, just use that. Okay. Okay, is that good?
Yes.
All right, well, thank you all very much. I'm going to be talking to you about is kind of a high-level overview, so we'll cover a lot of ground on uses of cryptography or cryptographic methods in economics. And my presentation was prepared with my colleague, Madars Virza, who is a research scientist at the Media Lab here at MIT. Okay, so let's see if I've got this right. So we start from the fact that there are inherent constraints on the design and functioning of any kind of market. One is unreliable private information. So that could be the fact that I have information and strategic reasons to withhold it, or to not report it accurately. There can be limited communication, either in the form of because you know that I have strategic reasons to not give you accurate information, it kind of degrades the value of that information. Or another dimension is that we have a large market, and I'm not aware of many of the other traders in the market. And then finally, these lead to situations where there can be limited commitment. For example, there may be a trading mechanism that is such that it's optimal for me to reveal, say, private information truthfully, but if I don't trust the mechanism, I think somehow my information will be exploited by the mechanism, then I may not divulge it. So examples, in auctions, you can have leakage of information. The auctioneer can be related to a bidder and can be communicating information on other bids to the bidder, or potentially can be misreporting the outcomes of the auction. In insurance, if there's an unverifiable loss, without cryptography, I'll show you in a few slides how it can be solved with cryptography, you can't insure it because the insured part. So for example, suppose there's somebody who wants to insure the value of their holdings of Bitcoin. And the loss would be, I lost my private key and I had this many Bitcoin. How can those things be verified? Therefore, how can you insure against it? In financial markets, you have a circumstance where you have brokers intermediating trades. You could increase the profit of the traders and the brokers by through conveyance of information about the preferences of the ultimate buyer and seller through the brokers. But as I'll explain to you in a few slides, there are incentive constraints that prevent that from happening. So the best we can do with markets are that they're constrained efficient, meaning that there's some Pareto improving trades that will not occur. A Pareto improvement is a rearrangement of trades such that at least one party is better off and nobody else is worse off. And one of the fundamental theorems of economics, the first theorem of welfare economics, says that an equilibrium in a competitive market is Pareto efficient, meaning that there's no potential to rearrange trades in any way such that it meets that condition. But these inherent constraints tell us just the opposite, that we can never attain a Pareto optimum allocation through competitive markets so long as these constraints are binding. Now, in some environments, constraints could be relaxed with trusted third parties through reputation, for example. But the use of cryptography that we've been focusing on are aspects that basically create trust as a mechanism to overcome or relax some of these constraints. So, for example, cryptography prevents the leakage of information. If we go back to the auction example, the bidders can become confident that their bids, if they're encrypted, will not be decrypted by anybody and can't be taken advantage of. There are smart contracts that can incentivize the revelation of unverifiable information. That is mechanisms such that I will agree to give I will follow or sort of maximize my gains by truthfully revealing through encryption my information, again, being confident that it can't be exploited by some competitor. And we can also overcome limited commitment. So we can use cryptographic methods to transcend classical constraints on market designs, which opens a possibility of creating new mechanisms to improve allocation. And I've just given a reference. There's Rob Townsend is a professor of economics here. He couldn't make it here today. Who's a leader in this field. And Nicholas Sang was at MIT, who's now at the IMF, and they recently published an overview of some of the preliminary views on these methods. Now, one interesting thing about MIT is on the economic side, what's really, in one sense, one way of thinking about it is we're going back to work that was done in the 1980s on something called the revelation principle, which is the idea that you have a market where people have private information and you're designing mechanisms, designing a market so as to extract that information to get them to report truthfully. And there were results, but very little implementation because there's still the trust question about the mechanism. Now, there are three principal figures in the revelation principle development, two of whom are at MIT in the econ department and who are involved. Well, one is Professor Townsend, the other is Bengt Holmstrom, both of whom are involved in this effort. On the cryptography side, the key aspects of cryptography that we are using were primarily developed at MIT. So this is a place where these two areas of research are converging. And in fact, my background's in economics. Madars Virza, the co-creator of these slides, is a cryptographer here. So one of and the other thing I should mention is that it's not, privacy is important, but it's not encryption. We've been living with encryption for decades. It's computation on data. That's what we're exploiting. So the methods that we're using, one, zero knowledge proofs. Alice can prove to Bob that she possesses data satisfying certain properties without revealing. So for example, a bank could prove to its regulator that it meets its liquid asset requirement without revealing other items on its balance sheet, or a collateralized loan issuer proves that it hasn't cherry-picked loans that it's putting into some loan pool. Next is fully homomorphic encryption, which enables arbitrary computation on encrypted data. So for example, a data holder can encrypt its data, give it to the cloud so that the cloud can compute on the data while not being able to decrypt it. And importantly, anybody can reproduce the computation. So you can check to make sure that the mechanism, or what I'll sometimes refer to as a smart contract, is correctly and as anticipated computing results. And then multi-party computation is a framework where you have a group of parties, some or all of whom possess secret information on which you want to compute some function and you want to issue outputs. It can be different information to different people. It could be an auction where everybody who's participating in the auction actually have to come together to complete the computation. And what comes out can be selective. And so that's another tool that we use. Now, there's an alternative to these methods that are, quite frankly used, which is a non-cryptographic hardware alternative, which is a trusted execution environment. That has, for example, as compared with fully homomorphic encryption at the present time, cost advantages. But the cryptographic methods rely on math, and they rely on provable math results. Whereas the hardware relies on, I suppose, experience in using the hardware and trust in the manufacturer of the hardware. But it's, I would argue, a lesser standard, though still sometimes useful because of cost advantages. Okay, so I'm going to go through 3 examples. An auction is a protocol for allocating an item as a function of bids. For example, in a Vickrey auction, bids are private and the item is awarded to the highest bidder, who will pay the second highest bid. So the appeal to the auctioneer, the people designing the auction, are that it's a framework that will elicit this kind of behavior under ideal conditions. And one can think of, for example, government auctions of rights to drill oil or spectrum and so forth, or any number of things. You can imagine online auctions for advertising and so on. So the winner will pay slightly more than the second bidder, and the secrecy of the bid is essential. So 2 problems that can emerge are, one is the leakage that we talked about, and the other is potentially collusion among bidders. And the third, which I've just mentioned before, is this idea that maybe the auctioneer is also improperly computing the results and isn't actually awarding to the highest bidder. So cryptographic solution is to have the bids encrypted. And a smart contract, or MPC, is computing the winning bidder. And the outputs can be whatever you want. So maybe that all that gets reported is the winning bid, not the losing bid, so you don't know what anybody else bid. You can do it any way that you want. So there's no leakage of bids from the auction protocol, but it still might be possible for agents to collude, either by sitting at a desk together as they input their data, so each can see that the other one is not taking advantage and is following the rule, or using zero-knowledge proofs on the encrypted data that they've submitted. The most interesting example is this one, is insurance markets, to me personally. So an insurance market contract pays out when a loss occurs. And to date, the loss needs to be verifiable. You have homeowners insurance, there's some damage, you've got an assessor that comes out, claims assessor to your house to survey the damage. You have medical insurance, you have a hospitalization event, that's verifiable. You have, a derivatives contract, which is a form of insurance. And if it's you're trading some asset that's traded on a market, everybody can read off of what has happened to the price of that asset, which determines the obligations that the parties have under the contract. But a private loss cannot be verified. So, the data loss that I lost costs X dollars. I might be able to insure against the event of having my data hacked. And I might have a contract where somebody's willing to give me a fixed payout based on some premium that I pay, but it can't be sensitive to the value of the loss. Or the Bitcoin example I gave you, or another one is a bank has a liquidity shortfall. It could announce that, but it won't, because it doesn't want to have a run or some other bad outcome. So these are the problems, that the unverifiable loss creates an incentive to overstate the claim. And the desire for privacy, as in the bank case, creates a fear of leakage if the loss is disclosed. So the cryptographic solution is complicated in the sense that there's a computation underneath. There's a linear programming problem that's pretty intensive that needs to be solved. But intuitively, the way it works is the claim. So we're now talking about ensuring where you couldn't before, where there's some loss that's not verified. I lost my Bitcoin key, and here's the amount of value of Bitcoin I had. So I encrypt my claim and send it to the smart contract. And the payout algorithm, the contract's running a payout algorithm that turns out to be a partially randomized mapping from the set of everybody's claim. And so what that means is that I don't know, I can verify that the algorithm is being run properly, but I'll never see what the other claims are. And I can't infer what the other claims are because there's this element of randomization. And so this can all be done masking the results. And the result is you can set up the incentive such that a policyholder's payout is maximized in expectation by stating the true loss. And this goes back to the revelation principle work that was done in economics in the 1980s. And importantly, the payout can be imperfectly correlated with the size of loss, meaning the higher, so I get a result where I'm not incentivized to overstate my loss, and yet the payout that I get is going to have some correlation with the size of my loss. It can't be perfect, because if it was perfect, I'd just state the maximum every time. But you actually can get this result where there's imperfect correlation. And so that opens up the possibility to expand insurance all over the place in areas that couldn't be insured before by use of cryptography. And this goes back to work that Professor Townsend did in the 1980s. So final market I want to talk to you about is a brokered financial market. So think of, I don't know, okay, good, I can move this. So what we have, the BD stand for broker dealers. So we have BDA with a client A, and we have BDB with its client B, and we have an object that's being traded, T, think of treasury, and the dollar signs money. And so what happens? A's client wants to sell a treasury for money. So it enters into a transaction with its broker. The broker sends it money, gets the treasury, goes into the interdealer market where it meets broker B, and makes a trade there, sells the treasury, gets money. Because all that A wants to do is to intermediate the trade, get a profit margin for doing it. And B, same motive, B has a client who wants to purchase the treasury, so B sends the treasury to the client for money. So this is like just a very simple schematic of like how a financial market operates. Now, there can be some limitations on achieving this first welfare theorem Pareto optimal outcome. We assume that neither of the broker dealers want to carry excess inventory, and they have some objective. I wrote in here both want to maximize trade. It could be they want to maximize their joint profit. It can be whatever objective you want to write in. Problem is they can't trust each other to truthfully report their client supply demand functions. So in other words, the brokers are meeting saying, oh yes, I've got a client, and I'll trade you, certain number of units of T for a certain amount of money. But if they have that discussion with each other, if A thinks, well, B is going to show up with or let's say B knows that A is going to show up with a large volume of treasuries, I'll show up with a small amount of money, and I'll force A to sell cheap because he doesn't want to hold on to the treasuries. It could be worth more to him. You can get those kind of strategic games being played. That this is an intuition. And that can lead to multiple equilibria where, A is anticipating that B is going to show up with a small amount of money, and therefore it makes a commitment to its client or purchases a small amount of treasuries. And you can just end up with a situation where all four agents in this chain would prefer and be better off to have a higher volume of trade. And yet the equilibrium, because of a coordination problem, prevents that from taking place. Furthermore, and this is essential, the profit is ultimately determined by A and B, by the clients, right? And so the other thing is the broker-dealers, another way of saying what I was saying before, have reasons to not truthfully report everything about their clients and know that about each other. So one of the ways that you can overcome that is by having the brokers send a deposit into the smart contract, and then send their client supply demand functions. It's like a list of for each price, how many treasuries will I buy or sell into the smart contract. And the smart contract can then match according to whatever the optimization criteria is, and then pay out. You have the objects, the clients will send the objects into the smart contract, or you can have, if you can have it that the smart contract will bind everybody to contracts that they sign. And you can overcome this information problem. And this is something I wrote with Professor Townsend as part of my PhD thesis. So now I want to go to another use of cryptography. And here we have like a schematic. I'll explain to you the details of a financial market. And what we're addressing here are two things, okay, in this. One is, since the 2008 financial crisis, there's been a movement among regulators in the US and other countries to force financial market trading onto clearing platforms. There are a number of reasons why, but one is because the regulators feel if all the trades are happening on these platforms, they can see what's going on. They can see when there are defaults. They can see when there are delays in payment. They can see who's defaulting and who's delaying, and they can have like an early warning system to come and intervene and act and prevent there being some contagion event that, where one party's default leads to a cascading set of defaults, which is something that happened in the financial crisis. What we're showing here, one thing we accomplish is that you can have, in certain circumstances, a decentralized. So there are efficiency losses in forcing the trades onto a common platform. And what we're saying here is you can have a decentralized market and still give the regulator the same quality and timeliness of information that they would receive on a central clearing platform. The other thing that's going on here, again, I'll walk you through this, is that you can also, if this information is being aggregated, say in a smart contract, you can compute potentially in certain circumstances a retrading. So everybody enters into their initial trades, it all gets pushed up to smart contract. And then there's this evaluation of how you can restructure the trades to achieve a Pareto improvement. And then you send new contracts back to everybody. And the traders will be fine with that. Because like, okay, I entered into one kind of trade and under a contract, and now I'm being given a replacement contract that I'm either indifferent to or will make me better off. So what is going on here? The agents, I to J, are the participants in the market trading. M is a message. That can be a contract. That can be a proposal. If the objects are tokenized, that can be the money in the treasuries, if we think about the objects of that kind of market. And so what happens is like agent, and then an SK, each agent has a secret key and a public key. So agent I is sending some message up to the mechanism operator smart contract. It will encrypt the message with the public key of the mechanism operator. So it gets to the mechanism operator. And the mechanism operator might be sending a message back. Remember, it could be a contract, it could be a treasury or money, to agent I, doing the same kind of encryption. Now we can get network privacy because you can structure the messages such that, A is going to send a message to the smart contract whenever it wants to. But in addition to that, it's going to be instructed to send empty messages. So you can put noise in. So if this is all on a public network, an eavesdropper can't make any kind of inference about the trading that's going on. So you get network privacy. Okay. And you have you can use zero knowledge proofs to audit the trades that the participants are engaged in. And so you have information on the contract, you have information on the trades, you can make inferences about defaults, delays, all the things that you get in central clearing. So that's where zero knowledge proofs come in. And then at the smart contract level, you can, now this is a protocol I'm not going to walk you through in detail because it pertains to, it's a particular application to the repo market. But the point is what's going on in this space is this evaluation and restructuring of trades that would then go, contracts being sent out to the participants. In theory, this can be done with fully homomorphic encryption because you can do arbitrary computation. It might be more practical in today's world to do it in a trusted execution environment that's run by a trusted entity like DTCC that manages right now central clearing in US financial markets. But that's and so the other thing I should mention is that we are actually working with a research department of one of the largest financial institutions in the world in implementing on toy models fully homomorphic encryption on this intermediate financial market trading model and on the insurance model. But I cannot tell you who the entity is because there are elements of our contract such that hopefully in a month I can. Finally, we'll go to zero knowledge proofs. So in a zero knowledge proof, you have Alice who wants to prove to Bob, here's sort of a prototypical setup. She's got a password to a zip file that had data of some sort. It could be ownership in things. It could be whatever. And she wants to prove to Bob that she has the password to this file. She can open it. And so she wants to prove that she's got the password that can decrypt the file without revealing it. And the password has a lot of entropy. So there's no way that Bob is going to be able to figure out anything else. there's going to take too much computing power for him to run the computations to figure it out. So this is just sort of a prototypical setting. Where it might come up is and this is actually an example that Jim will be familiar with because we've actually talked about, is Alice wants to get a loan. Alice is has a credit score that she wants to convey. And so what's happened is, let's say she's applying for a loan, and to qualify, her income has to be in a range of $100,000 to $150,000. Now, Alice has a bank account where money has come in, and that bank account shows what the money was spent on. She doesn't want to reveal to the lender exactly how much money came in, and she doesn't want to reveal all the items of her personal life and what she spent on. But she can obtain from the bank a certified statement of her account. And then what she can do is prove to the lender that I in fact possess such a certified statement. And that statement, among other things, has information that my income was I put in between $100,000 and $150,000. Like, this can be done with zero knowledge proof. So there's you can start thinking about lots of applications for this technology. And finally, in homage to Madars, although this has other applications, who loves dogs, these are dog NFTs, okay? And the idea here is Alice has so you have these NFTs. There are 9 NFTs, and there are going to be 9 public keys. Let's say this is on the Ethereum blockchain. There's 9 public keys, and those public keys, each one attaches to an NFT. But for some reason, and I'll give you a reason in a moment, Alice wants to prove to Bob that she is the owner of one of those public keys, and therefore the owner of one of the NFTs, but she doesn't want to reveal which NFT she owns. Okay, she can do this with a zero knowledge proof. Now, you can translate this into like the collateralized loan obligation setting. So here are a group of loans, and I want to prove that, and let's say I'm the loan, the CLO issuer. I want to prove certain properties of these loans, certain characteristics. I'm aggregating things together. But there's elements that I'm not going to give you. For example, they could be home mortgages, and I'm not going to reveal to you the names of each borrower and make that public. I'm actually not sure in that world what is considered to be essential to conceal or not. So I may have given you an example that may or may not apply in the real world, but this type of thing. And I also want to show, although this example doesn't show it, that I've been collecting loans, but I'm not retaining on my balance sheet any of them. I'm either putting everything into the CLO, or I'm making a truly random selection. So I'm not cherry picking. And this is something, a use case for which zero knowledge proofs can help. So that's all I have. Thank you very much.
Any questions for Dan?
No. Well, thank you so much.
There are questions.
Oh, sorry.
When will this technology be actually used in like enterprise, like the timeline of it?
I think it's being implemented now. I couldn't tell you in exactly which. Oh, so for some of the use, well, like in auctions, okay, this technology was used in Dutch sugar beet auctions. But I was going to mention the Dutch sugar beet auctions in this example, but then I was told that it's no longer used in Dutch sugar beet auctions, and I don't know why. So, like, that's an example where it was used, but these methods are being tested and developed quite a lot, probably more in the space of cryptocurrencies, where there's a lot of experimentation, and the data's online. But I would say pretty soon, because the tools they're here. We have the tools.
Because my understanding is like it's very heavy, it's resource heavy, and also it needs a lot of preparation on the hardware and other environment. So I was trying to understand when would like maybe a large enterprise will be able to utilize this, because what you said makes sense, and I wish that everybody can leverage the technology. So I'm just trying to understand the timeline of when it would like for no large enterprise to be able to use it price-wise and resource-wise.
So I wish Madars was here, because he's a cryptographer. He'd better, but I know it's not in the case of fully homomorphic encryption, because that's very computation intensive. But I also know that we're involved as the supplier of economic problems to solve, not as the cryptographers figuring this out, that there's a lot of work being put into trying to figure out ways of reducing or making FHE computations more efficient. Now, there is in central bank digital currencies, application of zero knowledge proof technologies in ensuring privacy. And that's work that the Madars at the Digital Currency Initiative here has been doing, working with central banks on designs of central bank privacy preserving digital currencies for central banks. Yes.
It's more of a question for you, Don. The FHE, is there research on making that quantum safe?
Yeah, it's a different class of problem. So the encryption of static data, so that's one focus. That's I think the focal point for quantum computing. Fully homomorphic encryption, like homomorphic computation as a whole, I think it's still understudied in quantum, just because the mathematical structure itself is already very complicated, and migrating that to quantum, I think that will add even more difficulty.
Okay, we have time for one quick question.
You mentioned to preserve privacy, we insert empty packets. And I wanted to know, are those completely empty with no data, or was that noisy data, just randomized data inserted to those packets?
Okay, I'm not sure. Is this pertain to the sending of messages? Okay, so can you restate the question?
Yeah, so when you mentioned inserting empty packets to create noise, were those completely empty packets, or are they packets with random data in them, so they have random sizes, but they have special markers indicating that they're empty?
Well, that's a good question, and I defer to the cryptographers in the room to correct me if I'm wrong, but I think it would be sufficient to just have it null, because once you encrypt the data, you've got ciphertext that you can't open anyway. But I don't know if there's a particular reason to inject, like random information inside of the ciphertext. I don't know the answer to that.
Okay, thank you, Dan.
Okay, thank you.
Let's give it up for Dan.